Hello guys, this is George Kamiti. Welcome back to our channel, and we are analyzing columns and struts using Rankine's formula. Today we got a problem that says this. A hollow cylindrical cast iron column is 4 meters long with both ends fixed. Determine the minimum diameter of the column if it has to carry a safe load of 250 kilonewtons with a factor of safety of 5. The internal diameter is 0.8 times the external diameter. Take the ultimate crushing stress to be 550 newtons per square millimeter and a constant A 1 divided by 1600. We are going to begin with writing the Rankine's formula. And please guys, if you haven't subscribed, please hit that subscription button. We are going to appreciate. The crippling load by Rankine formula is usually given by the crushing stress multiplied by the cross-sectional area of a bar divided by 1 plus a constant A into effective length divided by the least radius of gyration, which are squared. Both the effective length and the least radius of gyration are squared. So what we are going to do, we are going to determine the cross-sectional area of this hollow cylindrical cast iron. And since this the column is hollow and it has a circular cross-section, the cross-sectional area will be pi over 4 into d squared minus d squared, whereby capital D represents the external diameter and small d represents the internal diameter. We are told that the external, that is we are told that the internal diameter, that is D, is 0.8 times the external diameter. So we are going to substitute this 0.8 D here where we have the internal diameter. So this is going to give us pi over 4 into D squared minus this small d is 0.8 D, and that is squared. So this will lead us to pi over 4 into d squared minus 0.8 squared is 0.64. Therefore, you have 0.64 multiplied by d squared. And this will lead us to pi over 4 multiplied by 1 minus 0.64 is 0.36. So we multiply that by 0.36 d squared. 0.36 divided by 4, that is 0.09. So we are going to have the cross-sectional area of this column being 0.09 pi d squared. So that is the cross-sectional area of this column. The next thing we are going to determine is the effective length. Now we are told that both ends of this column are fixed. So when both ends of a column are fixed, the effective length is given by half of the actual length. The length of this column is 4 meters. So we are going to convert 4 meters to millimeters. 1 meter is equivalent to 1,000 millimeters. Therefore, 4 meters, that's going to be 4,000 millimeters. So that's going to be 4,000 millimeters divided by 2, which is 2,000 millimeters. That is the effective length. Then from there we are going to determine the value of the least radius of gyration, that is K. And from this formula, moment of inertia is equal to AK squared, where A is the cross-sectional area, K is the least radius of gyration. Therefore, when you make K the subject, K is going to be the square root of moment of inertia divided by the cross-sectional area. Get the square root of that. We have the cross-sectional area, so we are going to determine the moment of inertia. So the moment of inertia of this hollow column will be given by pi over 64 into d raised to 4 minus d raised to 4, since this column is hollow. We are going to have this pi over 64 into d raised to 4. Small d is 0.8 capital D, so that is going to be 0.8 d, and then we raise them to the power of 4. So we are going to have pi over 64 into d raised to 4 minus 0.8 raised to 4, that happens to be 0.4096, and then d raised to 4. The moment of inertia will now be pi over 64 multiplied by 1 minus 0.4096, that is 0.5904 d raised to 4. So when you divide 0.5904 divided by 64, that happens to be 0.0009225. Then we have this pi, and we have times d raised to 4. So that is the moment of inertia of this column. So the least radius of gyration, that is k, will now be given by the square root of 0.0009225 pi d raised to 4. Divide this by cross-sectional area, which is 0.09 pi d squared. So k is going to be, this pi and this one are going to cancel out, d squared will cancel with d squared, and we are going to remain with d squared. Then 0.0009225 divided by 0.09, that happens to be 0.1025 d squared. Get the square root of that. So the square root of 0.1025 is 0.32. The square root of d squared is d. Therefore, the least radius of gyration will be 0.32d. 32d. Awesome. Good. So the least radius of gyration is 0.32d. Now that we have everything, we can apply the P Rankine formula, and we are going to have the crippling load by Rankine will now be equal to the crushing stress, which is 550 newtons per square millimeter, multiplied by cross-sectional area of this column, which is 0.09 pi d squared. That is the cross-sectional area. Then we divide this by 1 plus a, which is 1 divided by 1600. Therefore 1 over 1600 into the effective length, LE over K. LE is 2000 millimeters. So that's going to be 2000 divided by the least radius of gyration, 0.32d, and then we square both of them. So there somewhere we have been told that the column has to carry a safe load of 250 kilonewtons with a factor of safety of 5. And we know that safe load is usually given by the crippling load by Rankine, that is P Rankine divided by the factor of safety. Therefore, it means that P Rankine, the crippling load, will be given by safe load multiplied by the factor of safety. Therefore, P Rankine will be given by safe load is 250 kilonewtons, factor of safety is 5, and this is going to be 1250 kilonewtons. We are going to convert it to newtons since the crushing stress is given in newtons per square millimeters. Therefore, P Rankine will be 1250 multiplied by 1000 newtons, which will be equal to 550, that is the crushing stress, times cross-sectional area 0.09 pi d squared. Divide this by 1 plus 1 over 1600 into 2000 divided by 0.32, that happens to be 6250. 6250 divided by, we are going to have d, and then that is squared. So what we are going to do, we are going to divide both sides by 550 times 0.09 pi. So on this side they are going to cancel out, but on the left hand side we are going to have 1250,000 divided by 550 times 0.09 pi being equal to, we are going to remain here with d squared. Therefore we are going to have d squared all over 1 plus 6250 squared, that happens to be 39,062,500. This will be divided by 1600 d squared. So we divide that by 1600 d squared. So this will lead us to 1250,000 divided by 550 times 0.09 pi, that happens to be 8038. This will be equal to d squared all over 1 plus 39,062,500 divided by 1600, that happens to be 24,414. Then we are going to remain with this d squared. So this will lead us to 8038 being equal to d squared all over, when we add 1 plus 24,414 over d squared, we are going to have d squared plus 24,414 all over d squared, because the LCM is going to be d squared. This will result to 8038 being equal to d squared divided by this. We are going to multiply d squared by the reciprocal of d squared plus 24,414 over d squared, and that's going to be d squared times d squared all over d squared plus 24,414. That is what we are going to have. So when we multiply both sides by d squared 224,414, we are going to have this 8038 times d squared, that is 8038 d squared, plus 8038 times d squared, that's going to be 8038 d squared, plus 8038 times 24,414, that will be 196,239,732, which will be equal to d raised to 4. d squared times d squared, that is d raised to the power of 4. So what we are going to do, we are going to bring the results on the left hand side to the right hand side of the equal sign, and this is going to lead us to d raised to 4 minus 8038 d squared minus 196,239,732 being equal to 0. So that will form what we call a quadratic equation. So from the quadratic formula, we know that when we want to get the value of x, we usually use this formula: minus b plus or minus b squared minus 4ac all over 2a. So b is negative 8038. Here you already have negative, so negative and negative are going to be positive. In this case, we are looking for the value of b, not x. So going to substitute the x with the b. And now we try to squeeze my things in here. So this will result to d being equal to 8038 plus or minus b squared. B is negative 8038, so that is squared, minus 4 times a is 1, times c, which is 196,239,732. So that is what we are going to have. Then all this we are going to divide by 2a, that is 2 times 1, since a is 1. This will lead us to 8038 plus or minus 8038 squared minus 4 times 1 times 196, 239, 732. All that is going to be 849,568,372, which we are going to determine its square root. And then all this will be divided by 2. 2 times 1 is 2. So this will lead us to 8039 Actually, what we are going to get after solving this quadratic equation will be d squared, since this is d raised to the power of 4. Therefore, d squared will be equal to 8038 plus or minus the square root of all this is going to be 29,147.3. And then we divide that by 2. So what we are going to have is d squared being equal to 8038 plus, since minus will not apply, we are going to get a negative diameter, which 8038 plus 29,147.3, that is going to be 18,592.678. So to get the value of d, we are going to find the square root of 18,592.678. So when we determine the square root of that, we are going to get it as 136.35 millimeters. Therefore, the value of the external diameter will be 136.35 millimeters. So that is the external diameter. The internal diameter, on the other hand, we are told that it is 0.8 times the external diameter. So 136.35 millimeters, which happens to be 109 0.08 millimeters. Therefore, that is the external diameter. So, ladies and gentlemen, that's how we go about this question. Thank you for watching our video. Please do subscribe if you are not yet a subscriber. Thank you. Let's meet in yet another lesson.